professor of statistics at Harvard University, Radcliffe alumni professor at the Radcliffe Institute, Harvard University, and professor of computer science at the Harvard John Paulson School of Engineering and Applied Science. Her lab works on clinical trial designs and online learning algorithms for developing personalized mobile health interventions. She is a 2013 MacArthur Fellow, a member of the National Academy of Sciences and the National Academy of Medicine, both of the US National Academies. She is currently president of the Institute of Mathematical Statistics. I have been following Susan's work ever since I was a graduate student. Actually, I started to work in this area ever since 2007. That's also from a SAMSI workshop. So without further ado, let's welcome Susan.
Hi, everybody. Can you hear me?
Yep.
Yes.
We can hear you.
Great. And can you, what do you see? Do you see the whole slide?
Yes.
Oh, great. Okay, so thanks for that last talk. A lot of what Bo-An spoke about is highly relevant in this setting. And I think he will see the connections for sure, and I hope other people do as well. So what we're going to do is, I want to, so this is mainly about using sequential decision-making tools in mobile health, digital health, so where you're involving wearables, smartphones, and so on. And the team for this project is on this slide, Marianne, Sabina, and Peja. So I'm going to give you a one-slide overview of mobile health, and then we'll go on. Most of this talk is about speeding up a bandit algorithm. And it's about one particular problem that we're struggling with. So, so in mobile health or any kind of digital health where you have a wearable, some sort of sensor, the application delivers treatment actions. These are reminders, suggestions, and so on. And this happens as the person goes about their life. And these actions, these treatment actions, are intended to impact the individual in some near-time way, help them manage their current stress, adhere to their medication regime, and so on. This near-time response is called a reward, same language that Bo-An used. And then there's the individual state. So the individual state could involve the location, their current location, the weather outside, their mood, how well they've been adhering, and so on. And it turns out that even though individuals will often be in the same state, they respond to treatment actions very differently. And so there's this increasing interest in how we can go about personalizing the sequential decision-making that occurs by the mobile device. That is, learning individual specific policies that input state and output treatment actions. The big problem in all of this is these are very high noise settings. They're very uncontrolled settings. What I'm going to do first is just, we've already had a review of RL, but I'll give you a review of RL from a slightly different viewpoint, and then we'll go on to this challenge of the high noise, making it difficult to learn. So RL appears perfect for this setting. As we know, it's a subfield of machine learning, and the idea is that the agent observes the current state of the system, the environment. The agent then, based on that information, chooses an action. In our case, it's a treatment action, like a message. And then the environment responds with moving to the next state and also provides a reward. And one of the reasons why RL is so attractive in this setting is because we don't have mechanistic models for how individuals will respond to different treatment actions. And as a result, we want to learn only the parts of the system that we need to be able to make decisions. So in mobile health, the agent, of course, is the RL algorithm. The actuator is a smart device or a wearable. There's a lot of human-computer interaction involved in this problem. And the environment is the individual. And usually, this is not always the case, but in general, one starts with a bandit algorithm. And bandit algorithms, what they do is they ignore the delayed effects of an action. So how the delayed effects of actions occur in this setting? The way they do is they impact how the environment, the states that the environment moves to. So it's this, the next state is called S sub t plus 1. A delayed effect occurs by the action impacting that next state. And then later, and then the agent may not be in as good a state or is in a better state, and things proceed on. We're going to ignore that here. We're going to focus for this talk. We're going to focus just on the immediate impact of the action. That is the immediate impact of the action on the subsequent reward. And this is one way to manage the noise level, because you don't, when you ignore the delayed effects, you don't have to form predictions of the future impact of your actions, which tend to be very noisy. So RL algorithms, if they're online, can be viewed conceptually as being composed of two types of algorithms. One is a learning algorithm. This essentially, from the viewpoint of a statistician, is that this learning algorithm conducts inference about unknown parameters in some model for the data. And this may not be a complete model of the data. It's just whatever you need to learn in order to inform treatment selection. But it is a statistical algorithm, basically. And then there's an action selection strategy. And that is how the RL algorithm is going to update the policy to select the next action. And if you read across the RL literature, you'll notice that people mix and match these two components all the time. So it's, at least I find it really useful to look at it. Think of RL as always composed of these two types of sub-algorithms. In our case, we're going to be looking at a bandit algorithm, like I said earlier. And here, the learning algorithm is Bayesian. We're going to use Bayesian inference for the mean of the reward, conditional and state on action. And I'm using that notation, lowercase r of SA, to denote that mean reward. And the reason why I said automated, I'm making such a big deal about automated, is this algorithm can't have there's no statistician in the loop. You can't have someone watching over it. These algorithms are run in real time on individuals' real life, multiple individuals' real lives. The second part of the second sub-algorithm is this action selection strategy. And here we're using posterior sampling, which is where the Thompson sampling, one often calls that Thompson sampling as well, but I'll call it posterior sampling because it makes it easier for me to remember. And in particular, what the algorithm does is it calculates the posterior probabilities for each action that action leads to the highest mean reward. And then you get a multinomial, you get multiple probability for each action, they sum to 1 in general, and you randomize the next action according to those multinomial probabilities. So that's the action selection strategy. The probability, of course, is higher if the data evidence so far indicates there's the potential for that action to be useful, or the action has shown greater usefulness in the past. So a big issue here is how do you speed up learning? And I already indicated one way by simply ignoring delayed effects that will improve learning of this reward, the mean reward. Another way is to use the prior, and indeed, because we're using Bayesian inference, we do build a prior, and the prior is based on prior data on the similar population. A third way to think about improving the rate at which you learn is to pool data across individuals. Now, I already just said that individuals can respond very differently, even though they're in the exact same state. But some states, they may respond very similarly. And furthermore, there may be states for which when people return to them time and time again, they may respond very similarly. And so that's what we want. We want to take advantage of any similarities that there might be. And what we're going to do is use a classical statistical model called a mixed effects model. And I'm going to talk about it shortly. And it's going to have a Bayesian framework. So some notation here. S is our state, I is the individual, T is the decision time. In the study that the study that motivated this work, there were 5 decision times per day, and it was over many, many days. A, capital A, denotes the action, and R denotes the reward. For example, in physical activity, it might be the subsequent 30-minute step count. I'm just going to look at binary actions and make everything really simple. I'm going to actually act as if all of my individuals start treatment simultaneously. This is a gross simplification, and it opens the door to the fact that this is not the case opens the door to some interesting further work, which if I remember, I'll indicate. But these simplifications help me be clearer. So the mixed effects model is only in the learning algorithm. It's not in the action selection strategy. So here's an example of a classical mixed effects model, the ith individual at the tth decision time. You have some features of state in action. They can be basis functions. Depending on the amount of data you have, you can have more complex high dimensional features or fewer features. And so you see there's 3 terms in this model for the mixed effects. The first term is the Z beta. Z is the feature, beta is what's called a fixed effect. The second term is, again, a vector of features. Now it's multiplied times what's called a person-specific random effect. I is indicating the individual. And the UIs indicate how much these individuals may differ from the overall average effect, which is encapsulated by the beta term. And then the last term, the third term, is again the features times a vector of time-specific random effects. And these time-specific random effects indicate the variability in these time-specific random effects indicates how much the responsivity of individuals may vary across time. So you have both, you're picking up differential responsivity both across individuals as well as across time by these 2 what's called random effects, UI and nu T. And if you're familiar with mixed effects models, you should be thinking right now that there should be further generalization, but we're going to stay at this level right now. The random effects have some specified distribution. Classical mixed effects models, they have a normal, you specify that they have a normal distribution, and you see the variance term for UI, it's sigma super U, and the variance term for nu T, nu sub T is sigma super nu. And those variance terms, that's what indicates the larger they are, the more differential responsivity you see across individuals or across time in the latter case. The random effect, these mixed effects model stipulates that the reward is equal to this mean function plus some noise. So here you have 3 things that have normal distributions, UI, nu T, and the epsilons, the noise terms, all independent. So it's a very simple type model. It's been used to great effect for quite some time. Now, we're going to add Bayesian inference to that. So we're going to assume that the fixed effects, that is the betas, have some prior distribution. And you see, and in our case, the prior mean and the prior covariance variance matrix that comes straight out of prior study, data from prior studies. It's a very simple model, and it makes for highly stable, fast computation in general. So in our Thompson sampling bandit, the action selection strategy, as I said earlier, is this posterior sampling. And I'm just repeating it just to help me be clear. So you have an individual I at time tau, and they're in a particular state, lowercase s. Then what one does for this binary action space is you select send action equal 1, that is sending a message in our case, with a particular probability, P of S, S is the state, and that P of S is the posterior probability that choosing action 1 would lead to a higher reward than choosing action 0. And that's conditional on the data you have in front of you. That's D sub tau, that's the data. I gave you a definition at the very bottom of the slide, as well as all these variance components, the variance of the person-specific, time-specific, and error variance components. So it's as if they are all given to you. So I'm going to talk about a little bit more later about these different variance components and mixed effects models. But the natural question, if you're in computer science, is why are we not using a multitask model? It's the natural thing. Each task is an individual. And both mixed effects models and multitask models produce a measure of similarity. And that similarity determines how much you pool across. Well, it's a similarity for individual time units. So it depends on how those similarities determine how much the data is pooled in order to decide which reward is best or which action is best in a given at a given time for a given individual for a given state. So the simplest, if you're not familiar with multitask models, I'll just give you an introduction. The simplest multitask model one I can think of is where I look at baseline data from all my individuals. I do some kind of sort of clustering, say like I get 10 clusters. I assign each individual to one of those 10 clusters. Each person in a particular cluster, I completely pool their data, act as if they're all the same, mice in a litter. And I don't pool across data. Data from different clusters is never pooled. That would be the simplest version of multitask modeling. A more sophisticated one might use social networks between individuals, and that is the case by this really nice paper by about Gang of Bandits paper. If you Google it, you can find how they use a graphical model to determine similarities between users and thus how to pool data across users in order to learn the mean reward for each individual. Now we're going to use a mixed effects model, and we're doing this for multiple reasons. They also provide similarities between individuals. And in particular, those similarities are encoded by these variance terms. The relative sizes of the sigma, the matrix sigma super U, the matrix sigma super nu. Remember the matrix sigma U, that's encoding the variability in the person-specific effects, how much they'll differ from the population. The matrix sigma nu encodes the similarity or the variance in how much effects will vary over time. And then you have the residual variance. So the similarity is encoded by the relative sizes of these variances. And in fact, Bayesian mixed effects models are just Gaussian process models. That's all they are, except they have very low dimensional kernels. And these three variance components, the two matrices and the scalar sigma squared, are just parameters in the GP kernel. So all you're doing is you're parameterizing a kernel for a GP model. That's really nice because that means that GPs provide a really easy way for us to increase the flexibility of the model for the mean reward. Now, why not just go straight off to a more complex kernel with a GP model? The issue here is this is an area, and I work mainly in clinical trials, so this is all research-based. So the teams involve behavioral scientists, health scientists, And in mobile health and digital technology, these guys, these scientists, are experts at using mixed effects models. They are very used to encoding their domain expertise into these models in terms of the features, choice of features, as well as which feature should have random effects of different types. So this is another way we can speed up learning by indirectly encoding their domain expertise, at least via the simple part of the model that involves the mixed effects. Another aspect is that you get very stable automated calculations, because this is all normal conjugate prior normal setting. As long as you have particular values for these matrices, everything's great. The problem is these variances are, they determine the amount of pooling across time and across individuals, but we don't know their values, and one might try and learn them up front, which would be similar to a clustering in the multitask setting. What we do is we want to learn as we go. So, and the standard idea, if you're familiar with Gaussian process models, is to use empirical Bayes estimation. So in GP models, one often uses empirical Bayes to estimate the parameters in the kernel, often called tuning parameters in the kernel. Here they're the variances. And that's indeed what we're going to look at. So I'm just giving you the definition of the empirical Bayes estimator. What it does is it maximizes the distribution of the data marginalized over the fixed effect beta and the vector of random effects u and the vector of random effects nu. Now we got to do this empirical Bayes estimation, the updating for our variances repeatedly over and over again in an online setting. So it has to be highly efficient. So how did we come to this? This is like a summary slide to help me be clear. We came to this because we were we had a large physical activity study with wearables and a smartphone, and we were using a Thompson sampling bandit with a Bayesian mixed effects model. And we were able to add on, we were allowed to add on a number of users for which we would try this pooling idea. So we planned, the natural thing is, if you're familiar with GP models, is to use GPyTorch. GPyTorch is a phenomenal suite of algorithms, highly modularized. It is the state of the art, and it was developed for complex kernels. It does do an approximate empirical Bayes estimation of the unknown parameters in the kernel. But we didn't have access to GPUs. We weren't going to be able to use parallel computing in the actual trial. So we had to have an efficient implementation. So what we did in preparing to add these users to the existing study is we conducted a variety of simulated studies, 50 simulated studies for 32 individuals in each study over 10 weeks, 5 decision points per day. Things didn't go well. The empirical Bayes estimation in GPyTorch was very slow. It was, in fact, we actually ended up using GPyTorch in the real study, but we could only update the parameters in the kernel once per week because it just took too long in the real study for the computations to end. Remember, we don't have access to GPUs. So one of the things we asked ourselves is it possible to speed up the empirical Bayes estimation? That's what this talk is about. So just reminding you what empirical Bayes is. It means we're going to estimate those variance components. I listed them in the far right, upper right of the slide. You maximize the distribution of the data, a marginal distribution of the data. And the standard way you do this is you use what's the EM algorithm. The EM algorithm is really convenient here because you just need the posterior distribution of your fixed and random effects, beta, u, and nu, given your data at each iteration. And of course, you're going to have to do a lot of iterations, and you have to run your EM algorithm a lot. So you want to, and it has to be automated online. There's no statistician watching it. Anybody who does automated work knows exactly what I mean. So we need to be able to calculate these posterior distributions over and over again to be able to have the execute the iterations in the EM algorithm. We need really fast, stable computations. So abandoning GPyTorch, we looked at the form of the posterior variance matrix for our fixed and random effects, and you see it in green. It's kind of highlighted in green here. It turns out it has a very simple form. It's the inverse of really simple matrix in which you have a capital C is a rectangular matrix of all the features, and F is just a diagonal matrix. That's really nice. E is a block diagonal matrix. Everything just looks really like there's a lot of potential here for speeding up. And so what we were able to do is I'll show you, we're going to be able to take advantage, to improve the computation, we'll be able to take advantage of the sparsity in the lower right-hand corner of the inverse of this matrix. And we're going to only need certain subblocks within that matrix to execute. Furthermore, the computation ends up being really stable. And that's because one can come up with this very clever matrix B, just seems to come from nowhere almost. At least Marianne, the postdoc who worked on that, it seemed to me it came from nowhere, in which every needed subblock in the posterior variance matrix comes from a QR decomposition. It's very clever. So here's the sparsity. So here's the matrix. So this is the inverse of the posterior variance, and it's very sparse. All these clear areas indicate 0 cells. And this is a toy example of M users and tau time points, so it's very small. I just want to say in the study we were interested in, tau, the number of time points goes up to around 1,400, and the number of users was on the order of 50. So there's a big difference between the number of time points and the number of users. So, and we're really interested in this setting where that lower right-hand corner is essentially a block diagonal. And how do you take advantage of that to speed up the computations? That was the first part. And the second part is, so you see that block diagonal here on the left-hand side. And this is just for M equal 2 and tau equal 2, just so I could put it on the slide. And it turns out that where the X's are for the posterior variance, we don't need those terms. And this is a consequence of the normal model, the Gaussian model, and the way it looks in the likelihood. All we need is the terms, the A's that are in the non-X'd things. And what's really nice here, I don't know if you can see my hand, but all we need, the little pointer, we just need 2 inverses, essentially, 2 types of inverses, A super 1, 1, and A super 2, 2, comma T. That's all we need. And these are, it turns out, by clever construction of a B matrix, it turns out that these blocks can just be found by using parts of a QR decomposition. All of this can be found in the associated papers that I've given you references to, one of which is Marianne's paper here at the bottom. The title is at the bottom of this slide. So this speeds up things amazing, and it's just fantastic. So I'm going to just give you an example of how it does that. So the first approach is this streamlined empirical Bayes, and it works well for either the number of time points large or the number of individuals large. Actually, Marianne has developed, has done work with, of course, with variational approximations. So if both are large, we use both a combination of this streamlining as well as the variational approximations. But for right now, just one or the other is large. And we're going to compare it to 2 implementations of GPyTorch, one with just regular CPUs and then the other with parallel processing parallel computing. Now, again, I'm not speaking poorly of GPyTorch. This is a phenomenal suite of algorithms. It's just, it was developed for very, very complex settings. So here we have a setting where we have number of individuals, 150, and the number of time points, 10, 50, 100, 10,000. So you can see the results here in terms of speed of computation. The first column, SEB, Streamlined Empirical Bayes, is our method, and the last is with the parallel processing. In the middle is just standard GPyTorch. We get gross speed improvement. And part of the reason why we had to go down this path was GPyTorch was not converging for really large numbers of time points. So we were getting very concerned. Here's a little bit of an indication of the accuracy. Light green is the method that Marianne led the development of, and you see that most of the time the absolute error is lower for the streamlined empirical Bayes. So it was very promising. So what we did was we wanted to see, well, how does this impact the regret? Again, this is all prep for this next study. So we used the simulation testbed that we had used in designing the original study. And in this study, again, in this simulation, each individual has 5 decision times per day. It's all based on physical activity because that's the setting we were working in. And each little simulation has 32 users, and they're in the study for 10 weeks. And you see the picture, the x-axis is the week in the trial, the y-axis is the average weekly regret. That is the difference between an oracle and the actual implemented method. And there's 3 methods, one with our method, one with standard GPyTorch, and then one with GPyTorch with the parallel processing. And you see the speed is about the same for our method as with the parallel processing, but we get better regret, lower regret. And this is probably because GPyTorch, because it's meant to be so general, it uses a variety of approximations. And in this Gaussian setting, there's just really, you don't really need, they don't work as well in this Gaussian setting, and you don't actually really want to use them. This is my last slide. What's nice about this implementation of empirical Bayes as well as this GP approach is we don't need advanced hardware, which is great because we want to run these in real life clinical mobile health studies, and we will probably not have access to GPUs. Some big challenges are we want to include correlation across time, like autoregressive models and the time-specific random effect. And can we obtain stable computation efficiencies in that setting? Also, individuals, as I mentioned earlier, individuals actually come into the studies incrementally. So you have sequences of tasks and they overlap. And how do you do either a banded algorithm? How do you take advantage of that overlapping? There's, as Boan mentioned, when you talk about humans, they disengage really fast. And so you want to take advantage of the users, the knowledge you gained on prior users to prevent disengagement as users come in future. That's it. Thank you so much.
Thank you, Susan. Any questions for Susan and also for Bo?
Susan, that was lovely. Thank you so much. I had a quick question for Bo following up on your talk. In a 2-person game with multiple equilibria, how do you know that both players are playing the same equilibrium solution? What happens if they don't?
So you're talking about 2-player or multiplayer?
For simplicity, a two-person game with multiple equilibria.
Okay, so I mean that is one question. I think for some games we are able to prove its uniqueness of the equilibrium, and obviously if there are multiple equilibrium, there is a equilibrium selection problem. I think normally for zero-sum game, it's often I guess it depends. Most time it's unique.
Yes.
So yeah, I mean that's right. So there are different situations. Sometimes there might be a equilibrium selection problem.
Thank you.
Yeah, that's all I want to see.
But, you know, in a lot of human subjects type studies, each individual they have different goals and they compete sometimes. So that's why I think, at least my interpretation, maybe David didn't mean this, but my interpretation is you might have different agents with different goals and you want them to collaborate, and how do you manage that?
So yeah, I mean, in that case, it's pretty much like you know, it's a game, because for games, people, you know, different agents have different preference. They have different goals. So in that case, you have to zero. That's why game theory can be applied. They try to analyze the equilibrium, where in a equilibrium, so there are different solution concepts, equilibrium solution concepts. But for instance, take Nash equilibrium as one example, where nobody wants to deviate. I guess that's kind of a stable or outcome or something.
Yeah, yeah.
Thank you, Susan.
Yeah, I have a question for you. I really think this contextual bandits is a very promising approach for mobile health. I'm just curious, could you comment on why do you choose to use Thompson sampling? For example, there are other choices like upper UCB, things like that. So if you could comment on that, that would be great.
Yeah, these are clinical trials, and so there's a lot of stakeholders. And the goal, you not only want to learn, i.e. personalize, you also want to create a data set that people can do off-policy learning on. And off-policy learning is facilitated if all actions are chosen with non-zero probability. All feasible actions for that state are selected with non-zero probability. So the minute you start using UCB methods, all your exploration is due to internal variation. It's not from this external randomization, and you don't control it. So you would, if you want to do off-policy learning when someone is implemented UCB, you're going to have to make a lot of mechanistic assumptions, and that's fine. If I do think there's some settings, maybe insulin control, that where one has access to really good mechanistic models, but in general, we don't, you know, have that kind of access. So I personally would never use any kind of non-stochastic action selection strategy, because after the study's over, there's tons of analyses that people want to run. I mean, you know, as you know, right? I mean, people are going to want to run mediation analysis. They're going to want to run longitudinal analyses. I want to facilitate all of these stakeholders' goals. And also, my gut feeling, you know, this goes back to something Boan said. These problems are inherently non-stationary.
Yeah, we're working on something, not for mobile health setting, for some other settings of contextual bandit. So we use GPUCB. You're talking about GP here. So it turns out the GPUCB runs faster than Thompson sampling. That's why I'm asking. Maybe that can have some other advantage, but I totally agree with what you're saying in terms of the concerns for this off-policy evaluation. Yeah, thank you.
Yeah, you'll never get as good a regret. I mean, you may get, if you don't, so we even control the Thompson sampling posterior probabilities. We don't let them go to 0 or 1 in the algorithm. So we'll never get the regret that you would get if you let those probabilities go to 1 or 0 or you use UCB. We just won't. But that's, I think in long-term implementation, we're going to have to do something like that because of the non-stationarity.
Yeah, there's a lot of research going on for different types of non-stationarity. I guess for mobile health, maybe there's a particular pattern. So anyway, and is that study ongoing, or is it just a simulation study? Because I think for mobile health, the data are not really that many available.
Yeah, we have a big study. It's in the field right now, but the pooling project, that finished. That was only a small add-on study. But the bigger study, we're not pooling information across users, but it is using Thompson sampling, and it's using, actually, it's not really a banded algorithm either. We're using something closer to full RL in the bigger study.
Yep, good to know. Thank you. Any other comments, questions? If not,
Joe.
yeah, go ahead, please.
Joe raised his hand. I don't know if he wants to ask.
Yeah, I raised my hand because I had similar questions. I would think from a decision analytic perspective, it's not optimal to do Thompson sampling. I guess you would rather optimize something else, but to learn the process behavior, and of course to get more variability in the data that you can use later, it helps. Isn't that is that what you're saying?
Well, there are regret bounds for Thompson sampling. And they are, well, you know, regret bounds, they're very coarse, I have to tell you. From a statistician's point of view, they're just like so coarse, it's unreal. But to the first order, for simple kinds of Thompson sampling, you get the same sort of frequentist regret bounds. For more complex ones, I think it's an open problem. But so I don't, and that's mainly because you allow those posterior probabilities to go to 1 or 0, depending, you know, so it gets to eliminate actions in a more smoother way.
Would it also
yeah, you should look at Benton Van Roy's work. He has a number of papers about how he advocates for Thompson sampling over UCB.
Would it also depend on your sigma, I don't know, sigma U and sigma, what was that, sigma nu? Yeah. Would it depend on those? If you have probabilities?
If you're doing pooling, I think it'll depend on how good of estimation you do, because those determine the kernel, the Gaussian process kernel, and that determines the similarity between data. So if you do a bad job, if your kernel's a bad kernel for that problem, that could be problematic, right? That's my gut feeling. Yeah.
Very good presentation.
Okay. Thank you all for the interesting discussion. And because of time limit, I think we would conclude the presentation session for now.